In this video, we'll examine forced vibration of the single degree of freedom system, and we will look at dynamic instabilities that can occur. Once again, we're looking at our mass spring system. We assume that there's no damping. X is the displacement of the mass positive downwards, and the mass is being forced by some external force which is harmonic in nature. So we call it F0 times cosine omega t. Now, we know from the previous time we looked at this harmonic oscillator, and the link should be above if you want to go back and review it. But the equations of motion look something like mx double dot of t plus kx dot, plus kx of t, not x dot, is equal to the force F of t, which in this case is F0 times cosine omega t. Call that equation 1. And we also know that the solution of such an equation is a combination of the homogeneous and the particular part. So x of t is equal to x homogeneous of t plus particular of t. In the context of vibrations, the homogeneous solution is also known as the transient solution, and the particular solution is known as the steady state solution. So for the homogeneous solution, we assume a free vibration problem. In other words, we make this part equal to 0. Okay, so a homogeneous solution and that assumes that mx double dot, I'm going to leave out the t dependency just for shorthand, but it should be implied that x is a function of time. And the homogeneous problem, the free vibration problem, looks like that. Mx double dot plus kx equals 0. We'll call this equation 2. And we've seen that the solution to this, we'll call x sub h of t, is equal to c1 times cosine of omega sub n t, where omega sub n is the natural frequency, plus c2 sine omega n of t. And we can write that omega n is equal to the square root of k divided by m, spring stiffness divided by the mass. We'll call this equation 3 and equation 4. All right. So to find the particular solution, and I've shown this in a previous video, the link to which appears above. But to find the particular solution, we use something called the method of undetermined coefficients. I'm not going to go through it in huge detail here because I've done it in this previous video. But fundamentally, when we have a forcing function that's sinusoidal, either a sine or a cosine, we assume a particular solution of the form, and I'll use the constants d here, d times cosine omega t plus d2 sine omega t. And this omega in general is different from the omega n's. Those two omegas in general are different. Okay, we're going to show what happens when they're the same, and that's when we get dynamic instability. But for now, we're assuming in general they're different. So this would be equation 5. Taking the derivative of equation 5 with respect to time, x dot sub p of t is equal to minus omega d1 times sine omega t plus omega d2 times cosine omega t, equation 6. Okay, and then the acceleration, which is the second derivative, x double dot sub p of t is equal to minus omega squared d1, this becomes a cosine of omega t, minus omega squared d2 times sine of omega t. Call that equation 7. All right, I'm going to make some space here to continue on the same page. And now the idea is to substitute 7 back into equation 1, and then we equate the coefficients of the similar terms. So what does that mean mathematically? That means, let me write this out, substituting 5 to 7 into 1. Okay, and from that we get minus omega squared. Let's see how I want to group this. Okay, so d1 times k minus omega squared m is times cosine omega t plus d2 into k minus omega squared m times sine of omega t is equal to f0 cosine of omega t. So all I've done is I've substituted this into equation 1, and then I've grouped it. I've grouped everything that's multiplying d1 and everything that's multiplying d2. Okay, and now when we look at the method of undetermined coefficients, on the left-hand side we have a sine term. On the right-hand side we have no sine term, so the coefficient on the right is 0. So what does that mean? If I look at the sine omega t term, on the left-hand side we have d2 k minus omega squared m is equal to 0. Well, this just implies that d2 is 0. That is equation 8. And similarly with the cosine omega t term, we find that d1 k minus omega squared m is equal to f sub 0, since we have a term with the cosine on the right. Coefficient is f sub 0, therefore the coefficients of the corresponding terms on the left and the right must be the same. That's what that's telling us. All right, so this implies that d1 is equal to f0, f sub 0, divided by k minus omega squared m. That's equation 9. So the particular solution, xp of t, is equal to just f0 divided by k minus omega squared m times cosine of omega t. Equation 10. So all that's remaining is, I should have probably numbered this, but this equation here, which says that the total response, x, is equal to the homogeneous response plus the particular response. This gives me x of t is equal to c1 cosine omega n t plus c2 sine omega n t plus, we do it on the next line, plus f0 divided by k minus omega squared m times cosine omega t. Now, one thing to notice is what happens mathematically if you cast your mind back to your calculus courses, your differential equation class. What happens if this omega was actually omega n? In this case, this would not be a unique solution, since these would just be the same terms. We would combine these coefficients, in other words, and it would say cosine omega nt. What we would need to do is, if omega is equal to n, then of course this would become an omega sub n, and then we would have to actually multiply this whole term by t. Okay, and that makes it unique and also a solution. So in other words, if omega were equal to omega n, if we were to force this simple harmonic oscillator at its natural frequency, amplitude would grow linearly with time. And that is the nature of the failure of the dynamic instability. All right, I'm going to try and draw that on the following page. Do it straight. And then this line is approximately x equals t. Draw its reflection below. On this axis we have time, and on the vertical axis we have x. Let me change color for this. We expect the function to look sinusoidal and growing. The amplitudes are growing linearly. Something like that. My drawing is not the best, I apologize. But the idea is that this is a linear growth phenomenon. Unlike the exponential growth we saw in the case of the static instability, dynamic instability is a linear growth phenomenon. Well, that brings us to the end of this video. I hope you found something useful in it. If you did, please go ahead and give it a thumbs up so that others can get to see it too. Or better still, go ahead and subscribe to the channel, and that way you'll be notified of any new videos that are released. If you have any questions, I'd love to hear from you in the comment section below. Thank you very much for watching, and I'll catch up with you in the next video.